All right, everyone. Thank you so much for joining me today on Rocks for Jocks. Adel Asadi and I overlapped for some time in graduate school together when I was doing my master's and he was doing his PhD. Adel has done a lot of really fascinating work in machine learning, specifically with applications to geohazards and mining. Adel right now is doing his postdoc at Stanford University, which we're going to learn a lot more about today. So, Adel, thanks again for joining us.
Thank you so much, Alex, for having me.
Great. So the first thing I want to get into here is a little bit about your background. I'm wondering if you could tell us a little bit more about how you decided to get into the machine learning work, which you're doing now.
Yeah, of course. So I think the story starts from the high school era of my life. At that point, when I was living in Iran, it's not like the US that you have a lot of opportunities and you can follow whatever you like. You also need to think about the job market and choose your major accordingly, not only based on your interest. So at that point, there were two major routes that I could consider. All those engineering degrees, which in Iran falls within the physics and mathematics major during the high school. The other route is the natural sciences, from which you can go the route of medical schools or related majors. So based on my interests at the time and courses that I was better at, I chose the engineering path. When it comes to the choice of program for undergraduate studies, as you know, Iran is a resource-rich country, including oil and gas and minerals, and one of the career paths with good opportunities in the future was, for example, petroleum engineering. At that point, I decided to study petroleum engineering for my undergraduate study. Then when I started undergrad school, my next goal was to think about what I'm going to do after my undergraduate study. And among the different paths, I chose to continue my studies abroad because of the circumstances of life and career in Iran, and also because in higher education like master's and PhD, the schools abroad were of higher quality for me to continue my education. And so I had a few countries and a few programs in mind for continuing my education, and the US was the target number one. At that point, because of the sanctions against the petroleum industry of Iran, I couldn't plan on continuing my education in petroleum engineering because of the visa restrictions and problems. The closest major that I could think of was mining engineering. And mining engineering is similar to petroleum in multiple aspects. Both of them deal with underground resources, and to study these two majors, you don't need a lot of different qualifications. So that was one thing I had in mind, and to achieve that and to find a spot in a university in the US, I needed to do some research during my undergraduate studies. And at that point, I talked to a few of my undergraduate professors, and they recommended that I work on data science and artificial intelligence, machine learning, for problem solving in petroleum engineering. And at that point, I had a professor of drilling engineering, and he has some specialty in geomechanics as well. And I started my research from that point, probably the second year of my undergraduate study. And I remember that I started with learning MATLAB programming and then how artificial neural networks work, basic and primary steps. And that led to a few conference presentations and papers. And finally, I could get admission with research assistantship from Michigan Tech University, where I studied my master's in mining engineering, and I did geostatistics and machine learning and artificial intelligence research there, which led to where I am right now. So these were the initial steps that brought me here.
That's great to hear. Honestly, I didn't know about a lot of those steps before we had this conversation. It sounds like you were already working on some pretty advanced topics in your second year of undergraduate. Did you have a heavy math background or anything by that point?
No, I didn't have, and I primarily did self-learning. I studied with reading a MATLAB programming book at that point. It got me started on MATLAB programming, and then I had a professor who could minimally at least supervise me on doing some basic research. I'm not talking about high-level research or solving complex problems, but I think it was good at that point for me to establish myself as a person that is interested in data science and solving problems using those type of tools. And I could present my findings in a few conferences, including international conferences. I traveled to Austria at that time during my undergraduate and presented my research there. And it was good for me to build my CV as an undergraduate who is interested in higher education. Because of the financial difficulties and the very high exchange rate between our national currency and the US currency, it wasn't possible for me to continue my education on my own funding. And those types of research experience helped me convince a professor at Michigan Tech for a fully funded master's position.
That's incredible. And then how did you find the Michigan Tech program?
Yeah, so at that point, I was interested in modeling and Earth resources engineering. And also, I was interested in a few related topics in civil engineering, including geotech. But I prioritized mining, and within the mining, I was looking for professors who do statistics and data science and AI. At that point, I found Dr. Chatterjee of Michigan Tech, who is an expert in geostatistics and data-driven modeling in the mining industry. And he works on multidisciplinary topics within mining. He does remote sensing, even for mineral mapping in other planets. And he also does underground reconstruction of deposits using geostatistical simulations. He does mining automation. He has some multidisciplinary interests and expertise, and I found him a person very interesting to work with. I had a few communications with him. It took several months for him to find funding for me, and then he reached out and offered me a position. I had a few other positions in mind, but some of them I wasn't successful in getting because most of the professors in the US don't fund master's students. The primary amount of funds generally goes to PhD students in the US. And that was a very hard thing for me. I was replied several times by several professors that we fund PhD students, not masters, including Tufts. Actually, I also applied to Tufts and I got rejected at that point.
Oh, no.
Because in my application form I said I only accept my offer if it is funded.
Oh, wow.
And and because of those difficulties, I didn't have a lot of options. I ended up studying my master's at Michigan Tech.
Awesome. Something else I want to highlight for listeners is that I think you said that your advisor at Michigan Tech was working on potentially mining for other planets. Was that right?
Exactly, yeah. He is also a remote sensing expert and he works with national and international space agencies in the US and in India, and they map minerals and geochemical components and also other aspects like landslide mapping and related stuff in different planets, including mainly lunar surface and Mars, as far as I know, yeah.
Yeah, I have a similar story as well. One of the graduate students at my undergraduate university, he was working on geology for Mars, and it blew my mind that people were actually studying Mars in that kind of depth already. So I just wanted to make sure I highlighted that because I'm sure some other people will find that interesting as well.
Exactly, and that was the reason I got interested in remote sensing during my master's, and that was one of the reasons I reached out to Lori. I knew that she was doing a lot of remote sensing damage mapping, and at that point, probably Vahid was the leader in that aspect in Lori's group, and I was so interested that I reached out to Lori, and inquired if there is a position for me to study PhD there.
Great. So then can you tell me a little bit about that transition from Michigan Tech to doing the PhD at Tufts?
Yeah, so I can say that I love data in general. It's not that I'm committed to a single discipline or a major of a study, but I love data. I love data science. I really like exploring data sets and get insights from them and make data-driven decision making and do a statistical modeling and analysis and whatever comes within that domain. So I was open to new domains. I wasn't that much committed to mining industry. At that point, I was thinking that I may pursue an academic career, and mining industry is not an appropriate discipline to pursue academic careers in terms of funding. For example, national labs and governmental funding are not interested in the mining world. At least they haven't been so far.
I didn't know that.
Exactly. A lot of mining professors have the problem of receiving funds and grants from the governmental agencies, including my Stanford professor, who is a mineral exploration expert, and he is funded totally by the private sector. He is working with a consortium of national and multinational companies, and they're all funding our research. As far as I know, his efforts to receive governmental grants from national labs have not worked so far.
Interesting.
But on the other hand, Lori's research is well funded by the government, and in general, civil engineering has much more opportunities in that aspect. If you want to pursue an academic career, there are a lot of national labs and agencies that fund civil engineering research, including geotechnical, as we have been receiving during my PhD at Tufts.
Yeah, that makes sense. So then tell me a little bit more about the PhD. Even though geohazards was not your primary interest, it seems like you still carved out a really good niche for yourself in terms of the remote sensing and machine learning work that you were able to do for Tufts. I guess I was wondering if you could tell me a little bit more about that. I have some notes as well on some of the papers if you wanted to talk a little bit more about any of those specifically.
Yeah, sure. As I mentioned, I'm mostly interested in developing tools and methods and solving problems rather than becoming an expert in a specific discipline. That's what I have been desiring so far, and I think it's been working well in terms of like enjoying my career. And I'm also interested in learning new things, and that also works well when you change discipline, change the school, change teams, and you become interdisciplinary when you do that. I think it has helped me also to transfer knowledge from domain to domain. For example, I've learned a lot of things during my master's that I could apply during my PhD and also during my first postdoc at Tufts. And right now I'm learning a lot of tools and learning from experiences of our team in mineral exploration. And these tools can be applied in Lori's research. And I'm thinking of collaborating with her later when I have time and apply these there. This is something I really enjoy. And during my PhD, I think for the first few months, I didn't have a specific topic to work on. Fortunately, my advisor, Professor Bays, was open to exploring new areas, and it wasn't a defined project for me. So I could explore different aspects and see which one I like. At the time, she had enough funding to support me because sometimes they have established funding from a specific project and you need to accomplish that project goals. But fortunately, it wasn't like that for me. The two geohazards that Lori's group were interested in were liquefaction and landslide. And I tried to be involved in both. I did allocate 2 chapters of my PhD to liquefaction and 2 chapters to landslide. And these constitute the 4 chapters of my PhD. And for one of the chapters, I tried to go the route of geospatial modeling, which is modeling hazards based on different geospatial parameters. And the other 3 chapters, I allocated it to remote sensing and image processing. Again, I tried to keep my chapters as diverse as possible to learn new skills and solve problems of different nature. And within those image processing aspect, I tried machine learning and deep learning. And for the hazard modeling project, I tried merging different machine learning algorithms to improve their overall performance. Maybe we can talk about those chapters if you are specifically interested in any of them, or maybe I can give an overview for each, whatever you recommend.
Yeah, I guess do you want to maybe start with your favorite and then we can take it from there?
Yeah, maybe my favorite chapter was my chapter 1. The reason that this chapter is my favorite because it was a really hard problem to solve for our group. It started with receiving a very good set of imagery for the uh, earthquake, which happened in 2011 in New Zealand. And we got a set of high resolution images, 10 centimeter spatial resolution, which were taken airborne. And we were aiming to develop a liquefaction mapping model out of them. But the problem was that those images were not labeled for liquefaction features. They were labeled in large scale with large polygons covering very large areas. However, we wanted to map liquefaction spatially, and we wanted to map them in a way that we have the boundaries of liquefactions and where the features have occurred on the surface so that we can apply it later to new events. When it came to the labeling part of the study, we encountered a big challenge. It was so hard to label them in a limited amount of time, and it was also subjective. Any person would label them differently. For example, we had different types of liquefaction. They were looking dark or light. The boundaries most of the time were not clear. Even sometimes we had different opinion about whether this feature is liquefaction or not. That was super challenging. Our groupmate, Christina Sanon, took the lead on the labeling part. She formed a group of undergraduate students to do the labeling. At that point, the challenge was the time-consuming aspect of the work and also the different standards each person had. This idea came to my mind that how can we automate this labeling process before we even go for the modeling? Because we needed the labels to do the modeling and to develop a model, but the labeling itself to train a new model was challenging. And at that point, I tried to develop a semi-supervised method that we can take advantage of for completing the labels of partially labeled image. For that, I took all of the already labeled images and polygons that were labeled by undergraduate students and double-checked by Christina for being standard and good quality. And then I tried to deal with the other features that were in the images. For example, we had buildings, roads, pavements, cars, trees, vegetation, soil, and all these needed to be recognized by any machine learning model that we wanted to develop. And also the buildings had different signature over the tile because the building roofs were of different colors, and it was challenging to deal with the buildings specifically. And for that, we took out the buildings first. Fortunately, there was some good quality geospatial building footprints for the area of study, and we took them out first, and then we dealt with the remaining features on the image. And for that, we needed at least one tile fully labeled for measuring the accuracy of our models, and that was also very challenging part of my research. I spent a few days, I remember, to fully label one tile very carefully and use that as the validation tile for that study. What happened was that when I fully labeled it, I realized that it has almost 5 times more liquefaction compared to the one that I received as partially labeled. So the goal of the study and the target was to go from that fifth liquefaction to the full liquefaction label. And I think it worked well for that tile, and we published the paper last year, which was a good achievement for one single tile. But still, there's a problem that the approach is a tile-based, and since the area is much larger than a single tile, I think Christina is now working on developing a more advanced deep learning method by taking advantage of active learning and semi-supervised, but for deep learning to expand it to the whole region.
That's such a cool process. Christina was on the podcast recently talking about her part in this project as well. It sounds like there were a lot of challenges when comparing labels between different people, like what somebody subjectively chooses to label or not label is tough to deal with. One note for the listeners, you mentioned semi-supervised labeling a couple of times. If I remember right, that's a class of machine learning methods where you can use a mix of labeled and unlabeled data. Is that right?
Exactly. In machine learning, we have 3 branches of supervised learning, unsupervised learning, and semi-supervised learning. So supervised learning is when you have data fully labeled. You can train any supervised algorithm that classifies the new pixels that are your testing samples into the classes that you had labels for in your training data. And unsupervised methods happen when you don't have any labels. Unsupervised methods, for example, include clustering algorithms. For example, you have a lot of data sets, like a lot of images of, for example, dogs, cats, cars, trees, and you really don't know how many type of objects you have in your data. You just want to cluster them into similar set of images. That's when you don't have any label. It's a fully unsupervised problem, and the methods related to the unsupervised problems are specific to those nature. And in between, there is an unsupervised approach which uses partially labeled data and tries to label the remaining data sets by taking advantage of the limited labeled data. And the way it happens is through an iterative process. For example, you have 10% of your data labeled. You can try to develop a model on that 10% and apply it on the other remaining 90%, and then only keep the ones that you are certain about. For example, if your model is probabilistic, you can assign a high probability of 95% and say anything that is higher than 95%, I want to keep it. Then you keep those portion of data, for example, from 10% labeled goes to 20%. And then you use those 20% that you have high confidence on and develop a model again. And again, in another iteration, you apply that developed model on the remaining 80%. And this process continues until all of your data are labeled. And the threshold can vary from case by case. And what Christina is probably going to do, which is another step ahead, I think, is to use active learning. Active learning means that instead of assigning a probability threshold and make this training process and labeling process automated, you take the role here. You as the model developer take an active role, and after each iteration, you look at the labels and decide which ones to keep and which ones to remove, instead of relying on probability or whatever accuracy criteria you have. And this is why it's called active learning. This is another type of semi-supervised learning that people use for solving such problems.
Great. So to summarize that project, it sounds like you tried a few different machine learning algorithms to complete the labeling of liquefaction locations in the imagery for that event. Would you say that's an accurate description?
Exactly, yes. Accurate description. That's correct. I took a comparative analysis approach in the paper. I compared, first of all, supervised learning with semi-supervised to show the benefit of semi-supervised learning for solving such problems. And also, I tried to generate a lot of features out of the color imagery that could help us distinguish liquefaction from other features. And I took a feature ranking and feature selection approach that we could only use the most suitable features for this purpose. And some of the features were shown to be more helpful, including statistical features derived out of the imagery. And that way we could expand our information, because imagery only includes 3 channels of red, green, and blue. But if you take different steps to extract new features from them using dimensionality reduction, dimensionality expansion, and also a statistical modeling of them, you can generate new sources of information that can be helpful in detecting the feature that you're looking for.
Awesome. Yeah, that makes sense to me. I appreciate how you're able to put this into terms that I can understand as well, because it's been a couple of years since I've seen a lot of this information. And also, I'm sure you have a much deeper level of understanding than most of us on these topics. So then moving on to some of your postdoc work, if I remember correctly, you did a postdoc at Tufts first, and then you're doing one at Stanford now. So I guess, do you want to maybe tell us a little bit more about that and kind of what your goals for each of those and what you're studying at each of them?
Yeah. During my PhD, I had a few industry experiences through 3 internships that I have in the mining industry. I also had a job offer as a geotechnical designer from a Stantec company. And during my PhD and maybe the last year, I was thinking of going to work in the industry. But later, when I was finishing my PhD and compiling my dissertation and working on my defense, I felt that that's not the route that satisfies me the most. I got interested in staying in academia, and Doctors Bays and Moaveni of Tufts offered me a postdoc position. It was a half and half position, half with Lori on the geohazards and geotechnical engineering, similar to my PhD, and half of the position was funded by Babak. It was related to wind energy. And at that point, Babak also was very open to the topic that I can choose, because the project was funded by NSF, and Babak mentioned that they are open to any topic that we think is appropriate. And because I was interested in remote sensing and geospatial modeling and image processing, I convinced him on modeling offshore wind. And the method that I wanted to use for modeling offshore wind was developed during my master's thesis. That's one of the examples that I mentioned about transferring knowledge from one domain to the other. During my master's, I developed a geostatistical simulation method, which is mostly developed for the mining sector. Mining engineers have been the ones who developed these types of algorithms, and they have been developed for several decades. The reason for developing such methods is to deal with the high uncertainty of modeling underground deposits. Using geostatistical simulation, they can generate multiple realizations of the same deposit and see how the uncertainty is quantified in different locations down the earth. So I used that approach and exploited it for offshore wind modeling. And because I was interested in remote sensing, I knew that I can exploit satellite data and model the offshore wind, which is also interesting to the offshore wind energy sector, because when they install turbines, they monitor the wind speed and direction all the time, and they also want to predict it. So I think it worked well in terms of defining a project that I like. And during my first postdoc at Tufts, which was a short tenure, it was only 8 months, I allocated almost half of it to the offshore wind modeling. And I used data which comes with multiple geospatial variables and tried to simulate the wind speed and direction. And the way I did it was by exploiting the concept of training image. I want to explain what training image is. Firstly, training image is the source of information that you want to reproduce. For example, you want to reproduce a gold deposit boundaries and grade under the Earth's surface. You need to know what patterns are common in that aspect. For example, a gold deposit might have different patterns than a copper deposit. And those patterns that you want to simulate are not known when you use traditional statistical methods. For example, if you use Kriging interpolation out of your drilling exploratory data, you get smooth results. Those are not natural patterns that occur under the ground. So in order to use those natural patterns when you are doing the simulation, the concept of training image was invented several decades ago. So you can use a training image that is developed by geoscientists that can represent what can happen in nature and what you want to reproduce in your simulations. And then I use those training images and use a stochastic modeling using multiple point geostatistics to generate different realizations and take their average as the prediction and take their standard deviation as the uncertainty. So for the purpose of offshore wind modeling, what happens is that we have multiple observations through history of the satellite observation. For example, I took 2 years of observations in the same location off coast of Massachusetts. I took 2 years of observations and stored them as my training image patterns. And then using lower resolution data, I tried to reproduce them by the pattern database that I stored out of those 2 years of history, and also the exploitation of clustering and dimensionality reduction that's a part of the multiple point geostatistical algorithm I developed during my master's study. Our preliminary results were promising, and we have presented it in a conference in the UK, and the paper is right now in progress and will probably be published hopefully next year.
That's really exciting stuff. Regarding the lab at Stanford, how do you like working with the team over there? Can you tell us a little bit about what that research group is like?
Yeah, of course. One problem that I had with Babak's group was that I was interested only in my own research, which was not a good thing. Because, for example, when I was in Lori's group, I was actively following others' research. I was actively following what Christina does, what you do, what Marshall does, what Leekon does, and they were all interesting to me. But when I joined Babak's group, because it was far from what I have done before, they were doing structural health monitoring and signal processing and the stuff that I wasn't familiar with and I wasn't interested in. One challenge for me to network in Babak's group and to make progress and make connections was that I learned from it that it's not only my own project that matters. I also need to be in a group or in an environment that I like as a whole. Working with Babak and our teammates, especially Eleonora, who was a postdoc at the time and who was supervising me, was amazing. I learned a lot from them, and they were also very engaging with what I've been working on.
That's great. And then do you find the Stanford group to be similar as well? Or what's that group dynamic like?
Yeah, here. So when I came here, I had the background of my master's in mining engineering and even my undergraduate degree in petroleum, which are helpful for me to understand what others are doing, at least to some degree. And also during my master's study, I even read a book by my current advisor at Stanford, which means that I was working on a very close discipline during my master's study. Yeah, exactly. And that's very interesting that I ended up coming here. Yeah, so we have a lot of common interests and mutual interests, and it's working well here as a group.
That's so good to hear. It seems like you have a really nice group that you're working with. Can you tell us maybe a little bit about what a typical week or month in the life of a postdoc looks like?
Yeah, of course. So I think postdoc has different aspects, although it also depends on the position. Some postdocs have, for example, even teaching responsibilities, which I don't have. Some postdocs could be purely research. Some postdocs are clinical, but I can talk about my own experience of a postdoc. For me, it has been almost all doing research, and I didn't even have considerable mentorship during my postdoc because some of the postdocs are expected to help undergrads, master's students, PhD students in their research. But for me, except the short duration at Tufts where I was working with other PhD students in Lori's group, here at Stanford, so far it has been only doing my own research. And so a typical week of a postdoc at Stanford consists of some group and personal meetings, which occurs for research progress and research discussions and planning ahead. It also consists of some personal and career development courses, which is really nice about Stanford because I've been studying at Michigan Tech, Tufts, and Stanford. So I've experienced three different schools, and I can say that it's significantly different at Stanford in terms of career development and personal development courses that are available here and you can attend. For example, since I've been here, I attended multiple courses like to know my own personality, how can I work with other people, how to do the mentorship, how to prepare myself for an academic career, a lot of geospatial workshops. There are a lot going on here that I can't even catch up. I fill my calendar with a lot of courses and events and I can't even attend them. This is one good aspect about Stanford. And the other thing is that here are some opportunities to think of which are not related to the research necessarily. For example, a lot of people here go the route of entrepreneurship and they establish their own startups and they run their own businesses and companies. That requires you to learn a lot of new skills, which you have not learned during your master's or PhD. And those skills are taught here at Stanford through different courses and initiatives. And many of the postdocs attend those and spend some of their time on those aspects. And in terms of research, it's mostly weekly updates to the supervisor and presenting research to the sponsors of our research. For example, I have a weekly meeting with the representative of the company that is funding my position, and I give them the latest updates of our progress and ask for their feedback, their suggestions, because we're working for them and we need to understand what do they need out of the money they are spending here. In terms of working hours, I think I'm working like 9 to 10 hours a day. And sometimes I also allocate my weekends based on the deadlines that I may have and based on how busy I might be.
Yeah, that all makes sense to me. Honestly, I thought you were going to say that you worked even more. I feel like you put out so much work for your time at Tufts. We all thought you were working like 15 hours a day.
That's
So there.
yeah, that's right. Yeah, I generally work more than is needed. For example, at Tufts, I could extend my stay at Tufts for probably a couple of years, but I'm always looking for what's going to happen next and try to like finish the job as soon as I can. I'm not a patient person.
No, that's a fine way to live. And then one thing that you said that was kind of surprising, I want to make sure I understood it correctly. So I know that there are a lot of startups and entrepreneurship in general at Stanford. I didn't realize so many of the researchers and even postdocs were involved in the entrepreneurship as well.
Yeah, exactly. That's the good thing about Stanford that I wanna highlight. It gives you multiple opportunities that you haven't been thinking of. For example, at when I was studying at Tufts, I was thinking of only two ways. Either I wanna stay in academia or I wanna work in the industry. But since I've come here, other opportunities have been clear to me, and there are specific paths that I can take. And the culture here is that the opportunities are limitless. For example, if you choose the route of entrepreneurship, everyone supports you, including advisor. For example, my advisor is paying the tuition for me to attend a business course. I'm gonna attend the course that is developed at Stanford called the Stanford Ignite. Is for people to learn how to run startups from idea to venture capital from the beginning. And when I talked to my advisor and showed an interest to attend this course, he immediately approved the funding. And
Oh, wow. That's
also,
incredible.
yeah, also there are a lot of resources at the Stanford Business School, and you can attend those events, learn from them. There are specific resources for postdocs who want to establish their own company. And the other good thing is that, for example, in our domain, one key aspect of being able to run a company is to make the connections needed, connections in the industry who could be potentially your first customers, right? Because if you want to develop your business, you need your first customers probably. And here you can make those connections because of the very strong connection between Stanford and industry. You can make those connections. And the other aspect is the capital rising. It's also facilitated here. You will be guided on how to pitch your idea and how to receive the capital you need to run your company. These are really facilitated here.
That's great. That's really cool stuff. I didn't realize how involved even the researchers were in the entrepreneurship space over there. So do you think you want to try something in that field next? Maybe some sort of startup or a small business?
Yeah, at this point, because I've recently started my postdoc, at this point I'm focusing on my research to firstly establish my place here and also get some exposure to the mineral exploration world and know people and do some quality research to show my capability in this domain. And then I will most likely think about that. Yes, I'm planning for it. And as I mentioned, I'm gonna attend the Stanford Ignite course, which will be helpful. My advisor has helped his previous students and postdoc running their own companies, and I may learn from them and my advisor himself. And one thing is that it takes time, so I'm not in rush for that. It takes time to do that, and for that I need to spend a good amount of time here at Stanford.
Yeah, absolutely. That all makes sense to me. Adele, I really appreciate your time with all of this. Is there anything else you want to share with the listeners before I stop recording?
One thing that I want to share, like as recommendations, is that being adventurous and trying new paths doesn't hurt. I think it exposes you to different opportunities and different career paths that you haven't think of before. The other thing is that problem solving itself, I think, can be really valuable rather than becoming expert in one specific discipline or domain. Because a lot of my experience tells me that a lot of problem solving experience and the tools and the methods that you develop in one discipline or domain can be applied elsewhere. And this is really interesting. So if, especially graduate students, for someone who studies PhD, the main goal should be to improve their problem solving skills rather than like knowing all of the details of a specific domain. For example, liquefaction, let's say as an example. I think the problem solving is more valuable. And if someone improves the problem solving skills and if someone improves also the personal characteristics that are needed for making progress in the domain, including networking skills, presentation skills, which I'm also still working on it. Those can be very helpful.
That all makes sense to me. I appreciate the wise words at the end, Adele, and I appreciate your time here again. Thanks so much, everyone, for listening.